Hello everybody and welcome to Mr. Saucedo's YouTube videos. Today we're going to be looking at the second part of chapter 14 in Zumdahl, the 7th edition, about acids and bases. So this unit, there's a lot in chapter 14, so we're actually going to have to split this into a third part afterwards, but we're going to get through a lot more of the math stuff today. All right, so section 14.4 about calculating the pH of strong acidic solutions. There are some tips and some tricks that we have to think about when we're looking at an acid-base problem. So the first question is, what are the major species in your solution? In other words, reactants, products. Remember, we have our balanced equations that we always have in a acid-base reaction. And so you really have to think about, are the reactants going to be the primary species in our beaker or in our test tube or whatever we're mixing it in? Or is it going to be our products, or is it going to be a mixture of both? And so depending on what is the dominant reaction that's actually going to be taking place, are we going to have an equilibrium that lies more to the left, or are we going to have an equilibrium that lies more to the right? Right? And so remember, in a strong acid solution or a strong basic solution, equilibrium lies essentially all the way to the right. And that means that we basically have completion, right? So the reaction has essentially gone to completion. And that's only true for strongly acidic or strongly basic solutions. For weakly acidic and weakly basic solutions, we have the opposite, where we have more reactants than we do products. Okay, so like it says, react all major species until you're only left with whatever's left, your equilibrium reaction. And so most of the time it'll have you solve for the pH if necessary. So we have a couple of concept questions here that really get to the core of what was on the previous slide. So let's consider we have an aqueous solution of 2.0 times 10 to the negative 3 moles per liter of hydrochloric acid. What are our major species in that solution, and what is the pH of that solution? Okay, major species. How do we figure that out? Well, we'd have to write a balanced equation for HCl and water. Okay, we'd have to write that, and then you'd have to look and see, is it going to be going to completion or not? The nice thing is HCl is on our list of strong acids. So since it's on our list of strong acids, it completely breaks apart. So that means that we're going to have complete ionization, essentially. And again, I normally write hydronium, H3O+, but you could just write H+. Cl-, we have chloride. And then, of course, water is going to be present in our solution. Okay, so those would be our major species in our solution. We would have complete ionization and water, which would be, whatever's left. Notice that HCl, the actual molecule itself, does not appear as a major species because it is essentially going to completion. There is no HCl in our solution at this point. We only have hydronium and we have chloride. So what would be the pH of that? Well, for a strong acid, it's really easy, right? All we need to do is take the negative log of whatever this says, and that's going to give us our pH. So the pH ends up being about 2.70, and that's just by taking the negative log of the concentration that we have in our solution here. So pretty easy, right? Now, I love asking this kind of question because you get all kinds of weird answers. Calculate the pH of 1.5 times 10 to the negative 11 moles per liter solution of HCl. So given that most chemistry students just immediately ignore what the question's asking and then just plug in numbers, if you were to plug this in, the negative logarithm of this, you would end up with a very large number. And most people would just stop there and say, okay, I'm done. In reality, though, the pH of this solution is 7.00, and I didn't even need to plug anything in. So think about it this way. I have HCl, and I have water, essentially, right? I'm dissolving HCl in water. That's what's going to give me my reaction, quote unquote, right? That's what's going to give me my ionization. Now, if HCl is a strong acid, it cannot have a pH that is less than 7. It can't. It's impossible. So if we were to plug in the negative logarithm of this, you would end up with a basic solution, a strongly acidic compound can never give you a basic solution. Even a weakly acidic, so like compound, cannot give you a, strongly basic or even basic solution. It cannot give you anything below 7.00. Now, why? Why is it not 10.82, which is what you would do if you plugged this in? Now, think about this. Essentially, you are adding such a small amount of HCl. This is a really, really, really tiny number that it ionizes completely, but there's so much more water in your solution that it's completely dilute. And so in reality, the contributing equilibrium is really the water. The water has the strongest equilibrium here. And since water, when it is neutral, has 1 times 10 to the negative 7 moles per liter of hydronium ions, that must mean that is the overwhelming equilibrium that's giving us our pH here. Now, always read and ask if your answer makes sense, because if you ever get something like 10.82 as your pH of, a strong acid, it could never happen. So you really have to think outside of the box and think, okay, what's actually going on here? Therefore, it would be neutral. I like to explain this. This would be like having a bathtub full of water and adding a drop of HCl to that bathtub full of water. It's not really going to change the pH. Okay. What about calculating the pH of, nitric acid? 1.5 times 10 to the negative 2 moles per liter nitric acid. Again, nice and easy. Nitric acid is a strong acid, so I just need to take the negative logarithm of whatever it's given. 1.82 is what that would end up being. Now, weak acids are a problem. They're a problem for everybody. It's the bane of all AP chemistry students' existence, and that's because solving for weak acid equilibrium requires more work. Okay, first thing you should do, still list all your major species. Remember, for a weak acid, we have mostly a leftward equilibrium, meaning a reactant-favored equilibrium. We're not going to have a lot of ionization. Choose the species that can produce H plus and write a balanced equation for it. Again, all of that stuff is exactly what we've been doing this entire time. If it gives you an equilibrium constant, now we can decide again which equilibrium is going to dominate. Remember, we don't even give equilibrium constants for strong acids because they're essentially infinite. So the only time Ka would ever become a really important thing would be if we're looking at a weak acid or a weak base. You write your equilibrium expression. You list the initial concentration. So we're doing an ICE diagram, an ICE diagram again, right? We need to define our change. That's our C. That's going to be our X. We're going to write our equilibrium concentrations, right? So that's the E in the ICE diagram. We're going to substitute the equilibrium concentrations into our expression. We're going to solve for X. Okay, now, this is where it gets a little bit easier than when we were dealing with equilibrium expressions in Unit 13. So when we were looking at just K and not Ka, we had to do quadratic equation stuff. And everybody hates doing the quadratic equation. But, and so here's our trick for weak acids and weak bases. We can solve for X an easier way than using a quadratic equation, and that is because our equilibrium concentration, the amount of change that we get, our X, is going to be so minusculely small, we can just ignore the minus X part of our ICE diagram, and we can just assume that the equilibrium concentration is exactly what was given in the problem as the concentration of HA. That means no quadratic equation. When can we make this assumption? We can make this assumption if the Ka is less than 1 times 10 to the negative 3, which thankfully for weak acidic solutions, it's normally going to be less than 1.0 times 10 to the negative 3. It's called the 5% rule. Sometimes that's what you'll see in a book. It'll kind of say, hey, figure out if you can use this trick. We're going to say that we can always use this trick if the Ka of the acid is less than 1 times 10 to the negative 3, which most weak acids fall into that group. And now we can calculate the H plus and pH if necessary. Let's do one. And this is why, like I said, we're going to have to split this into 3 videos. So how would we solve this problem? We have a weak acid. We have hydrogen cyanide here. We know that the concentration is 0.80 moles per liter. We know the Ka. Let's go through all of the steps and figure out exactly what's going on. So first, what are our major species in our solutions? Well, here's our balanced equation, right? So I would have to write HCN plus H2O. H, this is our acid, that's going to be our base. The H is going to donate here and make hydronium, that's our conjugate acid, and we're going to be left with just cyanide, that's our conjugate base. So what are our major species? Because HCN is a weak acid, it's this. HCN and H2O, that's going to be the majority of the species in our solution. Remember, weak acids, because they ionize to such a small degree, we're going to have less than 1% of this. Most of our solution is going to be this. Okay. Why aren't, there are a bunch of hydronium ions and cyanide ions in our reaction? Well, I kind of just said that. So since the solution is a weak acid, we can always assume that the equilibrium is to the left. And actually, I'm going to go back to the previous slide again. You can even see here the Ka value is a small number. And since it's a small number, that means that we are going to have a solution that is mostly reactant favored. All right. So these are our two possible reactions, right, that are going to contribute to the overall equilibrium of our solution. So we have this one up here, and then we have just water. Okay, just good old water here. Which reaction controls the pH? Well, thankfully, right, it's this. Normally, the way it works is that if the Ka value is larger, that is going to be the major contributing factor to our overall equilibrium. And notice that for water, it's 1 times 10 to the negative 14, whereas here it's 6.2 times 10 to the negative 10. This is not really necessary. Like, you don't really need to go through this step because it's giving us this for a reason. If this were, if this were trying to trick us, really, this would not be a good way of tricking us because it's giving us a Ka value that is clearly bigger than this for water. And so, of course, this is going to be our major contributing equilibrium. So remember, larger Ka means that it's more likely to happen. And so this is going to be our more likely equilibrium that's happening here. So now let's actually go through and calculate the pH for one of these things. All right. I have 0.50 moles per liter of hydrofluoric acid. It gives me the Ka value. Hydrofluoric acid is incidentally not a strong acid. Most people assume it is because hydrochloric, hydrobromic, and hydroiodic acid are, but it just so happens that fluoride and hydrogen stick together extremely well, and that's probably mostly because of the electronegativity of fluorine being so high. So in reality, the H doesn't donate as easily as you would assume. And so the Ka is 7.2 times 10 to the negative 4. What's the pH? We need to go through all of the steps. What are the major species in our solution? HF and H2O. Again, it's a weak acid. That means that our reactants are going to be the major contributors to this. So we're going to have mostly a reactant-favored equilibrium. I do need to write a balanced equation for this. So again, we have two choices, right? The balanced equation can be this, hydrofluoric acid manufacturing a fluoride ion and hydronium ion, or we could be looking at a situation where we're looking at, water reacting with itself, self-ionizing. Obviously, this is our winner, and the winner exists because we have a Ka value that is way different than 1 times 10 to the negative 14. All right, now we need to set this up in an ICE diagram. All right, so what's our initial amount we were given? 0.5 moles per liter. What's our change? We don't know. Essentially, this is 0. And so we're adding x to this. Now, remember, our shortcut said that when we're writing our equilibrium expression, right? So our equilibrium expression doesn't include liquids, so water is not included. So we have our Ka value equals hydronium ion concentration times fluoride ion concentration times hydrofluoric acid concentration. So great, that's fantastic. But remember, we do have a trick here. Since we have a Ka value that is less than 1 times 10 to the negative 3, we can actually ignore this minus x here. So in reality, this is just 0.5. So when I'm plugging in our values here, I plug in x and x, so it's x times x, that's x squared, divided by 0.5. I don't need to worry about this minus x, which means I don't have to have a quadratic equation. So let's plug that in. So I have x squared divided by 0.5. I can multiply these two together and set them equal to x squared. When I do that, I get x squared equals this, 0.00036. On the bright side, I can just take the square root of both sides. Yes, this is supposed to be a square root symbol. So in case you're wondering, there's just no line over the top. What is the square root of 0.00036? It ends up being about 0.019, which means I can just take the negative logarithm of that. And when I do that, I get a pH of about 1.72. A very long process to get this answer, but way nicer than in Unit 13 or Chapter 13, where we had to solve a quadratic equation in order to get something. All right, so just keep that in mind. That is our big trick that separates what we did in Chapter 13 from what we did in what we are doing, I guess, in Chapter 14. All right, percent dissociation, also known as percent ionization. Now, the percent dissociation of an acid is equal to the amount of dissociation divided by your initial concentration times 100. So for strong acids, the percent dissociation is 100%. These values end up being the same. For a weak acid, they're very different amounts. The initial concentration you get is going to be very different from the amount that actually breaks apart. And so like it says, for a given weak acid, though, and I know this doesn't make a lot of sense, but the percent dissociation increases as the acid becomes more dilute. And again, when you're picturing that in your head, because it doesn't seem to make a lot of sense, just think about what these two values would be if you added more water to it. Okay, so let's actually calculate this for something like formic acid. I have 8 molar formic acid, and that's what formic acid looks like. It has a 0.47% ionization rate in water. What is the Ka value for formic acid? Let's solve for this. And I'm just going to use question marks instead of an X because later on I'm going to be using X in my ICE diagram. So I don't want to confuse you. So if I know the percent is 0.47 and I know my initial value is 8, I can basically find this amount here by just solving for it. So let's solve for the question marks. That's pretty easy. We end up getting 0.0376 moles per liter. Okay, now I can make an ICE diagram where I can utilize that as my change. Okay, so here's formic acid and water, hydronium ion, and then a formate ion. All right, my initial value was 8. I know my change. I go to 7.96. And you can see this is why we're able to ignore that minus X when we do weakly acidic solution kind of problems like this, right? This isn't a very big difference. But it's going to make a difference when I plug it into my equation here and try to find the Ka. So I can write my, my equilibrium expression for this. It would be hydronium ion times the formate ion divided by formic acid. And so I can just plug those in. I can plug in both of these and I can plug in this, and that will tell me the Ka of formic acid. And look what it ends up being, 1.76 times 10 to the negative 4. Pretty useful. If you know the percent dissociation, you can actually find what the Ka of a particular weak acid is. Now, let's find the pH of this solution using the data from the previous slides that we just figured out. Okay, the pH of the negative logarithm of the change from the previous slide, right here, that's the amount of hydronium ion I have, right? Ends up being a pH of about 1.42. And that would be my pH for that particular solution. Now, the value of Ka for 4.0 m, is that going to be higher, lower, or the same as the Ka value for 8.00 molar formic acid? It's not a trick question. It should be the same. And this is because Ka only changes with temperature. A lot of times people have a misconception that these values are going to be different because we have different amounts that we're starting with. I'm starting with 4 here versus starting with 8 here. But remember, in reality, all that means is that my amount of hydronium ion is going to be proportional, and my amount of hydronium ion here was proportional to the initial amount. But it should be the same. Ka doesn't change except with temperature. Now, what about the pH? Is the pH value going to change if I have 4.00 molar formic acid versus 8? That should get higher. Why? Because again, it's proportional. So the amount of hydronium ion is less here. And since it's less, that means the pH is going to be larger. And remember, larger pH means less acidic or more basic. So of course, this has a lower concentration. The pH should get higher because that means it is a weaker acid. It's an even weaker form of the acid than 8.00 molar formic acid. All right, bases. This is where we're going to stop. So reminder for bases, we already talked about it in the last video, but Arrhenius bases produce OH minus ions. Bronsted-Lowry bases are proton acceptors. Okay, so that's the difference. Remember, Arrhenius acids are H plus producers or hydronium ion producers. Arrhenius bases are OH minus producers. Bronsted-Lowry acids donate protons. Bronsted-Lowry bases accept protons. In a basic solution at 25 degrees Celsius, the pH has to be greater than 7. POH is equal to the negative log of the OH minus concentration. The pH is equal to 14 minus the POH. Again, all of these were from the previous video. So let's figure it out. I have sodium hydroxide. Sodium hydroxide is a strong base. That means that I can just plug this in to get the POH. So the POH is the negative log of this number. That gives me 3. But remember, it wants the pH, so I'd have to subtract it from 14. So 14 minus 3 is 11, and that gives me my pH of sodium hydroxide here. Okay, the next one is a little trickier. Calcium hydroxide, also a strong base, but calcium hydroxide, remember, calcium is an alkaline earth metal. It is a +2. That means it has 2 hydroxides. So if I'm looking at it dissociating, it actually dissociates into 2 hydroxide ions. That means that this amount should actually be double if I'm looking at the number of hydroxide ions I have in my solution. So hydroxide should equal 2 times 10 to the negative 3 because I have double that amount. Everybody would make that mistake. So keep in mind, calcium hydroxide, all of your alkaline earth, your heavy alkaline earth hydroxides have double the amount of hydroxide because they dissociate into 2 hydroxides. So the POH would be the negative log of 2 times 10 to the negative 3. That gives me 2.7. That means the pH is 14 minus that amount, 11.3. Again, if you were not to have done this step, you would get 11, which would be incorrect. All right, let's do one last one. Let's take a look at an equilibrium expression now for a weak base. Remember that an equilibrium expression for a weak base, I still do not include liquids, only aqueous solutions. And we like to use Kb to represent the equilibrium expression for a weak base. So Ka was for acids, Kb is for bases. And just like previous ones, right, like the previous ones, water is not included, and we have our products over our reactant in this case. Now, pH calculations for weak bases are almost exactly the same. We use the exact same tricks, including, kind of our non-quadratic trick, which is always nice. So let's actually do this for a real example. So we have calculate the pH of 2.0 moles per liter of ammonia. Notice the Kb value is less than 1 times 10 to the negative 3. That means that I can utilize my shortcut of not having to do a quadratic, which is fantastic. Okay, so let's calculate. I have 2.0. That was my starting amount. I'm going to minus x from that. I do not know what the change is. But again, Ionization is basically, less than 1%, so it's going to be virtually zero for this, and so that's what I end up with. Now, I'm going to ignore this minus x right here because it's going to essentially be 2 if I round. So 1.8 times 10 to the negative 5 times ammonium times hydroxide divided by ammonia. So I can plug in an x here, I can plug in an x here, and I can plug in 2 here at the bottom. When I do that, I get x squared divided by 2 equals our equilibrium constant. Now, when I multiply these together, this is what I get. I can take the square root. Yes, again, that is supposed to be a square root symbol. I get a POH then. So when I take the square root, I get 0.0060. I can take the negative log of that in order to get the POH. The POH is 2.22. To find the pH, I take 14 and I minus 2.22 to get 11.78. And that is how you utilize, I know it sounds like a lot, right? And that is how you utilize equilibrium expressions for weak acids and weak bases. Notice they are exactly the same process. All right, so that's where we're going to have to stop. We only got through a couple of sections, but trust me, you'll thank me later when the last video probably is going to take about 20 or 30 minutes on its own. All right, so if you have any questions, obviously leave a comment, let me know. And part 3 will be coming out soon.